Okay, now here we've really pretty much wrapped up elementary algebra. We're moving into the intermediate algebra now. But this is the last little bit of elementary algebra. So we have this system consisting of two equations. We want to solve it. Now there are a couple of things we could do. We could graph the system, and we might learn something from graphing it. We'll talk a little bit about that, but right now we're going to solve it by elimination. And the figure I recommend is you number these equations 1 and 2 and write down what you're doing to each equation. Now, if I multiply the first equation by 3, so this means 3 times the first equation, 3 times both sides, we're going to get 12x minus 18y equals 6. And if we multiply both sides of this equation by 2, so I indicate that as 2 times equation 2, well, you can write out what we get. And everybody's going to be able to do that. But we're going to get negative 12x plus 18y equals negative 6. Okay. Now, first of all, how did I pick these numbers? Well, the least common multiple of 4 and 6 is 12. So in order to get 12 up here, I better multiply by 3. And in order to get negative 12 here, I better multiply by 2. Then my x's will be eliminated, okay? So go ahead and get what you add, get what you get if you add now the first equation to the second. Now the circle 1 and circle 2 always refers back to the last system, okay? So it doesn't refer back to the first system. Okay, so equation 1 is now this one, equation 2 is now this one. I can actually indicate that by saying 3 times this equation 1 gives you the new equation 1. And 2 times this equation 2 gives you new equation 2. So that this is now equation 1 and this is now equation 2. All this is an arrow pointing to the left. So we can always see which one is equation 1, which one is equation 2. So what do you get when you add these two equations? Okay, so what happens when we add these two equations? 12x and negative 12x gives us 0. Negative 18y and 18y is 0. We don't need a calculator to figure that out because they're equal and opposite. 6 and negative 6 is 0. So 0 equals 0. That's what we get when we add the equations. This is true. No matter what values we have, for x and y, it makes no difference what the value of x is, makes no difference what the value of y is. Okay, if this equation is true, this equation is true. Our conclusion is any values of x and y that solve the first equation also solve the second. Now, how do we represent the values of x and y that satisfy the first equation? Well, the first equation, 4x minus 6y equals 2, the x-intercept is 1/2. If y equals 0, x equals 1/2. So that here is a point one half 0. The y-intercept, if we work it out, is negative 1/3. So here are our intercepts. You sketch a straight line, and this straight line represents four x minus 6y equals 2. Every point on this line is a solution to the first equation. Well, that means that every point on this line is also a solution to the second equation. Since adding these equations gives us 0 equals 0, any value of x and y that satisfies one satisfies the other. Here's the set of all x, y points whose values satisfy this equation. For that reason, we conclude that the graph of the second equation is exactly the same as the graph of the first. Okay, so here's the graph of negative 6x plus 9y equals negative 3. Now imagine we've got kind of a thick line here that's half white and half purple. We have the same line. Every point on this line solves both equations. Every x, y point on the line solves both equations. Okay. Now let's look at what happens if we had, let's say, four x minus 6y equals 2, and negative 6x plus 9y equals 18. We can add multiples of these two equations. We can eliminate x exactly the same way. Here's equation 1, here's equation 2. Three times equation 1 is our new equation 1, and that's going to be 12x minus 18y equals 6, just like it was before. And multiplying 2 by the second equation, we get negative 12x plus 18y equals 36. Now, if I add these two equations, I'm going to get 0 equals 42. This is false. for any x, y. So the lines don't intersect, because if they intersected, there'd be a point x, y that solved both of them. And it can't be, because these equations lead to contradiction. So I'll write the word contradiction. Zero can't equal 44. If we graph these two equations, this equation has x-intercept -3. And y-intercept 2. We draw a line through these points, or attempt to draw through the points. There it is. Now, if we draw the line for 4x minus 6y equals 2, it's the same as the line we have here. It goes through 1/2, 0, and 0, -1/3. I didn't do a good job of hitting these 2 points, but you get the idea. It's the same graph we had here. Well, it follows that the lines are parallel, but they don't intersect. Okay, so what we have here, these 2 lines are parallel and they intersect. They're the same line. That's what you get from these 2 equations. These lines are parallel. Of course, parallel lines that don't intersect never meet. That's what parallel means. So we have parallel lines that non-intersecting. Okay. Now that's important stuff, and especially for some more advanced courses that build on this one. So we want to understand the geometry of this at this point. So toward the end of the course, we do something similar. We use a method of elimination with 3 simultaneous equations. And we'll see where that leads when we get there. And now we're going to talk about exponents. And this pretty much moves us into what we're going to regard here, at least, as intermediate algebra. Okay. First example of exponents. 2 raised to the 4th power means what? It means 2 multiplied by 2 multiplied by 2 multiplied by 2. Now, 2 times 2 is 4. You multiply that by 2, you get 8. You multiply that by 2, you get 16. Oh, can you write down what 2 to the 3rd would mean? Okay, so 2 to the 3rd means what? It means 2 times 2 times 2, which is 8. Okay. Well, it follows then that 2 to the 2nd power, or 2 squared, would just be 2 times 2, which is 4. And 2 to to the first power, what would 2 to the first power be? You sure we should figure it? It's 2. Yeah. Just be 2. Well, let's write it down over here. We've kind of got a list of the powers of 2. Now, we notice that to climb from one power to the next, we simply double the power that we have. In other words, if we have 2 to the 1, which is 2, to get 2 to the second, well, we've got to multiply by another 2. So 2 times 2 is 4. And 2 times 4 is 8. And 2 times 8 is 16. You count these in your fingers. This one, got to use your toes a little bit. We get it. Okay, so let's see. So what we're seeing is half of 16 is 8, half of 8 is 4, and half of 4 is 2. So we double if we want to go up. We take half if we want to come back down. So what would 2 to the 0 be? If we look at this process, we take half of each number and we get the next one. So what's half of 2? Half of 2 is not 0. If you got $2 and give me half of what you have, how many dollars do you have? 1. Half of 2 is 1. Half of 2 is not 0. Okay? We have each number go this way. Have meaning H-A-L-V-E, cut it in half. Well, that 2 to the 0 is written so badly, I got even to get smudged. I got to make it a little better. Okay. Now, what about these numbers? The exponents go 4, 3, 2, 1, 0, right? Now, if we're counting down, what comes after 0? 4, 3, 2, 1, 0. If we're counting along the number line, well, let's just draw that out. Okay, so here's a number line. Got 4, 3, 2, 1, 0. What are the next 3 numbers? Can you write the number line out? Tell me what numbers go here. Okay, so everybody got that. Did a nice job of it. You're going to have -1 here, -2 here, -3 here. Now, you might have known when I went 4, 3, 2, 1, 0, what comes next? You would know maybe that it's -1, but if you draw this out, you see why it has to be -1. Okay, so what's 2 to the -1? Well, not sure what to put here. But if we cut 1 in half, what do we have? We have 1/2. Got $1 and give me half of it. How much do you have left? $0.50. Okay. So this equals 1/2. Now, if this process continues, 2 to the -2 equals, just by cutting things in half, what's half of a half? Well, if you have now $0.50 and give me half of it, how much do you have left? You have a quarter of a dollar. And 2 to the -3, well, I'm going to speak just a little bit on the format of this. Okay, this has to be 1/4. So you cut this in half, which equals, but no, we're going to keep it 1/4 over. I'm going to write it over here. And that's kind of smudge. I'll write it here. 1/2 squared. because of course 4 is 2 squared. 2 to the negative 3 has to be half of 1/4. Now, if you multiply 1/2 by 1/4, then you have half of 1/4, and that's 1/8. And that's 1 over 2 to the third power. So what would 2 to the negative 4th do? Write out a line just like this one, but for 2 to the negative 4th and see what you get. Okay, great. Everybody got that almost instantly. It's 1 over 2 to the 4th. I have room to write it out neatly, but it's 1 over 16. Okay. Okay. So we have a rule. We're going to say, well, if it works for 2, we at least hope that it works for any other number. So we can say, well, first the rule for 2. 2 to the negative b is what? It's 1 over 2 to the b. So if b equals 4, 2 to the negative 4th, b would be 4, right? And you'd have 1 over 2 to the 4th. So the rule tells you exactly what we've written down here. Okay, the expanded rule any number with a negative b equals the reciprocal of that number raised to the b power. Now, this is a very important rule that, in my experience, pre-calculus students very seldom remember when they come into the course. I think they haven't solved enough problems. They haven't done enough drill to make that rule second nature. Okay. So it's a very important rule, though, especially when we start graphing what's called the toolkit functions. Now, I'm not going to do that now, but there are a handful of graphs that are very powerful. Okay. We can do a whole lot with them. Matter of fact, I'm reading some halfway advanced statistics right now. And almost all the graphs I see are toolkit functions or combinations of toolkit functions. Okay. And by seeing how those toolkit functions work, of course, I understand it because I've seen it, many times over the last century. Okay. But not quite a century. I'm convinced that students are going to understand it well if they can understand it geometrically. As a matter of fact, I showed the whole toolkit scheme to my grandson, who's an electrical engineer, to help him understand something that he was working on outside of his work. Okay. And he thought it was really good. Okay, well, anyhow, we get to that. All I'm saying right now is this is a very important rule for understanding those toolkit functions. That comes down the road. Okay. After you complete this course, if you're successful, you can take the F 161 along with the co-requisite MDE 61 course. And you're going to encounter this right away. Okay. Or very early in the course. Okay, well, that's one rule for exponents. Now, that's usually not the first rule you see for exponents, but I chose to illustrate it first. Okay. Now, let's see. What does it mean to write 2 squared times 2 cubed? Well, in parentheses, write what you'd write for 2 squared, and in parentheses, write what you'd write for 2 cubed. Don't calculate it, write out what it means the same way we wrote out what 2 to the 4th means, what 2 to the 3rd means, and all that stuff. Okay, now when I say don't calculate it, I mean, don't write 2 squared as 4, that's a calculation. Okay, 2 squared is just 2 times 2. Okay, what's 2 cubed? Well, should be obvious. And of course, if you wrote down the calculation, it's natural since you got these numbers over here to do that. Even though I said not to. So if you did, it's natural. Oversight. Nothing bad, but this is how we want to write it out. Okay. Now, I wrote this with parentheses around the 2 squared. This is 2 squared. And with parentheses around the 2 cubed. Here's your 2 cubed. Of course, all these are multiplied, so we don't need the purple parentheses. So this would be the same as 2 times 2 times 2 times 2 times 2. And what power of 2 is that? Okay, well, again, everybody saw this real quickly. And that's, you got 1, 2, 3, 4, 5 2s there, so that means you got 2 to the 5th. Okay. Okay, well, in general, to the A multiplied by 2 to the B equals I'll use purple parentheses around the 2 to the A. Multiply 2 by itself A times. Okay, that's what 2 to the A means. Now I've got 3 dots there indicating we don't know how many 2's there are, although I guess we assume there are at least 3. So we just keep writing 2's until we've got A of them down. You don't want to have to do that if you got like 2 to the 500th power. You don't want to write 500 2's, but you can visualize it. You can visualize 500 2's strung out here. So if A was 500, there'd be a lot of 2's in those 3 dots. Okay. And you multiply that by 2 to the B, which is 2 times 2 dot times 2. B times, and this equal how many 2's? Okay, so we use the example. If A was 20 and B was 30. Okay. Well, you're going to write down 2A times, that means 20 times. And you're going to write down 2B times, that would be 30 times. So if A's 20 and B's 30, you got 22's here and 32's here. How many 2's does that make? Well, 22's here and 32's here. If you write out 22's and write out 32's and count them, you can confirm that you got 50. That's 20 plus 30. Okay, so Okay, these are dots. They kind of look like minus signs, but they're dots. You got a plus b times, which means you got 2 to the a plus b. So if you have 8 to 2 to the 20th times 2 to the 30th, you see why you would have 20 of them here, 30 of them here. You'd have 20 plus 30 or 50 between here and here. And that's what you'd have here. It would be 2 raised to the a plus b power. So it's important to understand that. And then in general, or more in general, okay, x to the a times x to the b equals x to the a plus b. You can see that in our first example. 2 to the second times 2 to the third is 2 to the fifth. 5 is 2 plus 3. Okay. So I could even write this out. I didn't want to write it out with the 2 plus 3 here until we consider this idea. But it's 2 to the 2 plus 3. Because you got 2 of them here and you got 3 of them here. You got 2 here, you got 3 here. That's 2 plus 3 is 5 of them. And now there's a strong tendency to want to multiply. Say that 2 to the a times 2 to the b is 2 to the a times b, because here we are in multiplication. You want to understand why that's not right. So you don't write out x to the a times x to the b equals x to the a times b. It's x to the a plus b. Now there is a calculation that's x to the a times b, so we'll illustrate that. Okay, so let me ask you to write down what is 2 to the second raised to the third power. Okay, 2 to the second raised to the third power is, okay, let me do it the way most people did it. Really be done either way. This is 2 times 2 raised to the third. Well, there's a temptation to multiply the 2's and get 4, and you get 4 to the third, and that's right. But that's how you get the answer. That's not how you understand why. The rule is what it is. That's not how you're going to understand the rule. So, but still, if you thought of, okay, then that's 4 to the third, that would be. But what we want to really do is write 2 times 2 to the third means 2 times 2 multiplied by 2 times 2 multiplied by 2 times 2. When you raise something to the third power, you won't write it out 3 times and multiply. Okay. So what power of 2 do we have? Okay, so all we have to do is count the 2's. They're all multiplied by each other. There are 1, 2, 3, 4, 5, 6 of them, right? And we can even anticipate what we're going to do next. By saying that, how many 2's do we have? We have 6. Well, we have 3 groups of 2. 2 groups. So they're a pair of 2's in each group. That means there are 3 times 2 2's, which is 2 to the 6. Okay, there's 2, there's 2, there's 2. You got 3 groups of 2. That makes 3 times 2, which is 6. Okay, and then we can say, okay, two to the a to the b. Now I'm going to write it this way. It's 2 to the a You write 2 to the A, B times. Okay, so there are B groups. And each group has A twos. So how many twos do you have? Well, if you got B groups, and each group has A things in it, you've got A times B things. So here's where you multiply your exponents. When you have a power of a power, when you have something raised to a power and that raised to that, you have some number to a power raised to another power. You multiply the two powers. And then the general rule. Right down the wrong rule, didn't I? Rule is x to the a raised to the b power is x raised to the a times b. Well, now we have at least 3 words for exponents. This rule tells you what you do with the negative exponent. X to the a multiplied by x to the b is x to the a plus b. X to the a raised to the b power is x to the a times b. Now there's another rule that I'll let open math explain to you just for sake of time. It's if you raise x, y to the a power, well, that means you got x, y written out a times. Means you're going to have a x's and a y's. So you're going to have x to the a times y to the a. And another rule, which is really the same one, but not really. X over y to the a equals x to the a over y to the a. Now that's a nucleus of rules. There are a couple more we could write down, but you get those from open math. Okay, now don't bother writing down all of these, but write down the first one. Quantity 2x cubed. Okay, and what I really want you to do is look at these rules. Which rule would apply to quantity 2x cubed? Rule 1, 2, 3, 4, and 5. And you say 4, you saw it right away. Everybody got it? Oh, that's very good. So what do you get when you apply rule 4? Go ahead and write it out. Okay, now some people actually wrote this out. They said, well, okay, 2x, the third is 2x times 2x times 2x, which is the same as 2 times 2 times 2 times x times x. As you can, these are all multiplied, you can change the order of your multiplication, put all the 2's together and all the x's together. And that gives you 2 to the third x to the third. Now you didn't really need to do that, but it's always good to do that, especially if you got small exponents, just to convince yourself that the rule really works. Now, if you want to apply the rule, it's like x y to the a equals x to the a, y to the a, okay? Means then 2x to the third would be 2 to the third times x to the third. Okay? So if you got the a power of 2 things that are multiplied together, it's just the a power of this one times the a power of that one. And that's 2 to the third x to the third. And that's by rule 4. And this is by writing it out, reasoning it out. Okay? Now, if this was 2x to the 900th power, you'd be able to write 2 to the 900, x to the 900, just using this rule. Okay? And you wouldn't have to write out 2x 900 times. Okay? I know you can do that, but you don't want to have to do that. Take an hour. Okay. So, and I've got this 4 here. This is meaning that we just quoted rule 4. Okay. Now, what do you think you might do with 2x to the quantity to the third times the quantity 5x squared? So we could write this out. 2x, 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 5x, 5x. Okay. So you got 2 times 2 times 2 times 5 times 5. Times a bunch of x's. Okay. And you can come up with 2 to the third, which some people did, and 5 squared, right? And then what about x? X to what power? You got 5 of them written out here. You got 5 of them here. 6x to the 5th. Right? Now, the rules give us that. Okay? If we use rule 4 again, 2x quantity cubed. You just look at that, you say, well, that's going to be 2 cubed times x cubed. That would be this. And then this would be 5 squared times x squared. That's by rule 4. And this is by rule 4. Then, of course, that's 2 cubed times 5 squared. Times x cubed times x squared. Now I'm having to write that up here. I anticipated having this line here to do this. Since people are wanting to write this out, I'm going to take the space and we'll just leave with the fact that this is a little okay. But you've got an x cubed and an x squared, and they're multiplied. Okay, then x cubed times x squared is what? We've got this rule, x to the a times x to the b is x to the a plus b. That's going to be x to the 3 plus 2, which is x to the 5th. So I don't have room to finish this, but that's the way it works. You're going to see similar examples in open math. Okay, so what about x squared y cubed to the 4th? Let's do that using rule 4 without writing it all out, because it's going to get a little long if you write it all out. Okay, what does rule 4 tell us about x squared to the 4th, x squared y cubed to the 4th? The fourth rule tells me that if you got this times this raised to the a power, it's this raised to the a times this raised to the a, right? If you look at this means you got x squared raised to the fourth and y cubed raised to the fourth, okay? It's not just xy raised to a power, it's x squared, y cubed raised to a power. It's x squared to that power times y cubed to that power. So this is x squared to the fourth, y cubed to the fourth. That's my rule 4. That makes sense? Just says when you got a power out here, it applies to every term you have in here. So it's the fourth power of this, which is now x cubed, x squared, so x squared to the fourth, and the fourth power of y cubed to the fourth. And then what's x squared to the fourth? You got a power of a power. Which rule deals with the power of a power? It's this, okay? Rule 3. So it says when you raise one power of some quantity to another power, you raise that quantity to the product of the two powers. And you get, so this is about rule 3. And, you know, okay, x to the 8th, y to the 12th. Just multiply it out. So we want to be able to apply these rules, but we also want to be able to write it out if the numbers are small, you know, using expanding all the x's and y's and see why the rules work, okay? So you want to be able to apply the rules. So if I give you, let's say, 5x to the 8th, y to the 12th raised to the 20th power. Let's see if you have a good idea what to do with that. Okay, so what we do here, and there's a little bit of a curveball because we've got 3 things in here, but the idea, the principle here, and we could do it formally, we could explain why the principle works. Principle is, if you got a bunch of stuff multiplied in here, it's raised to the 8th power, each one is raised to the 8th power, okay? That means that 5 is going to be raised to the 20th power. And x to the 8th is going to be raised to the 20th power. And y to the 12th is going to be raised to the 20th power. Well, I don't know off the top of my head what 5 to the 20th is. 5 to the 4th is 125. 100 raised to the 5th is, okay, 100 billion, 100 billion, and got a little more than that. Probably got something like 400 or 500 billion there if you do that. Okay, well, we're not going to do it. But x to the 8th to the 20th let me write this out in 2 steps. Okay, x to the 8th to the 20th is x to the 20 times 8. 20 times 8 is 160. Y to the 20 times 12 will be y to the 240. Okay. So the rule, you can visualize writing all this out. You can visualize writing 8x's 20 times, and you can visualize writing 12y's 20 times, but you don't want to really have to do that. The numbers are too big. Okay. Now, 5 to the 20th, you can calculate with your calculator. Okay. That's a 100 billion. 5 cubed is 125. You're going to have 6 of those. That's going to be maybe 500 trillion. Then you still got 25 of those. So you're going to end up in the quadrillions. And it's going to be a big number you're going to do in scientific notation anyway. Okay, so point is, you leave 5 to the 20th with your calculator. Everybody needs to do that. And everything else works out. Now, the homework is going to have similar problems. They're going to get a little longer, but the whole idea, now, the ideas are no different than the ideas we're using here. You're going to see plenty of examples in the videos and so forth. So get that down, and we'll go a little further next time.